I'll begin with a word of prayer. So, Heavenly Father, we thank you that you loved us first, even when we didn't love you, Lord Jesus. We thank you for your grace and mercy to us this day. I just ask you bless this class, Lord. Help us to understand a little bit more about your creation together, Lord. In your name I pray. Amen. Okay, so I'm going to try to describe to you the notion of essentially triangulation of a space. In particular, I'm hoping to give you a quick overview of simplicial homology, and then just a little bit on singular homology, and how that ties into the theory of integration of forms. So the end of class, I'll probably do something a little bit more frivolous, but we'll see. Okay, so chapter 5, basically. So first of all, definition: a polytope is a convex hull of a finite set of points. All right, this is all happening inside Rn. Definition: in a fine hyperplane. Well, I don't need to go through that. We went through that last time. Basically, I'll give you an example rather than definition. If we look at, let's say, xyz in R3, such that the dot product of xyz with, let's say, abc is equal to d, this will define in a fine hyperplane in R3. In fact, this will define the plane in R3. And that's pretty easy to see, because if you look at this equation, what is it? It's ax plus by plus cz is equal to d. So the jibber jabber at the end of last class went, oh, what does this mean? Just an idiot. I mean, it's obvious what it is. There's the equation of a plane. And so if you replace this with an arbitrary pair of points and just the dot product in Rn, then it just defines. If you look at this in R2, it gives you lines. In R4, it gives you hyperplanes and so forth and so on. These define the affine hyperplanes. Now, basically, the affine hyperplane H is a supporting hyperplane of a polytope if it meets the polytope in some non-empty way. Let's say here. So, in a fine. So this is an affine hyperplane. If you replace this just with, x comma v equals to c, or let's say equal to a, that's his notation, such that x is in Rn, that gives you an affine hyperplane in Rn. And if you look at greater than or equal to a, that would give you a half space. Less than or equal to a give you the other half space. The two half spaces meet at the plane. It's all just, okay, anyway. So, in a fine hyperplane is a supporting hyperplane of an n-dimensional polytope. If, I need a name for it. Let's call it H for hyperplane. If H intersect P is non-empty. But more than that, and P is in some, half space defined by H. So probably the best thing to do is just to look at an example. Okay, like here's a polytope. Kind of a stupid one, but I'll look at n equals to 2. So this thing is my polytope P. the convex hull, right? The convex hull of the vertices, actually, right? If you look at all linear combinations of those 3 points with sums of coefficients which are 1, it's convex hull, right? So like if this is P0, if this is P1, if this is P2, a typical point in P, like here, let's say x would be equal to, you know, T naught P0 plus T1 P1 plus T2 P2, like that, where what? Where the sum of the coefficients are 1 and they're non-negative, right? By the way, these have a name. This T naught, T1, and T2, these are called the barycentric coordinates, which has a, has there's a lot to say about that in solid state physics, but I'll just leave it at that. Now, okay, so solid state physics is all about studying crystals and lattices of crystals, and so you can see how you can think about those as joined by their points and things. I mean, it's not too surprising what I'm saying. So a supporting hyperplane here would be something like this one. The hyperplanes here are just lines, right? And so if you look at this line, and this is the half space, right? H is the actual line. The half space is below the line. As you can see, the polytope fits in there. That's a supporting hyperplane. There are 3 supporting hyperplanes, right? I can't take a line that goes through the triangle. That won't work because it's not all on one side of the line. So pretty much just the supporting hyperplanes that line up with the edges, right? Oh, you're right. If I took the other kind of thing I could do would be like this. Yeah, you're right. I could do that too. You're right. It could just intersect in a vertex. That's right.
Does it have to touch the triangle? Or?
Yes. And again, it has to meet P in some non-empty set. All right, so this leads us to definitions of different things in a polytope. In particular, the intersection of the supporting hyperplane with a polytope is a face of the polytope. In particular, the 0-dimensional faces are called what? What are the 1-dimensional faces called?
Vertices.
0-dimensional face, vertices, yeah. The 1-dimensional faces are called edges. And then when you get to an n-1 dimensional face, we call it a facet. Right. All the facets together give the boundary of the polytope, all right? The text tells us that the polytope is the convex hull of its vertices, and each face is the convex hull of some subset of the vertices, but it's not a particularly easy thing to prove, as it turns out. All right. This is really just the initial language that we need. What computationally, the computational aspect of what we're covering really starts here. All right, so set of points. If we say S is a set of points, it's a finite set of points in Rn. So like P0, P1, PD, right? This is a finite set of points. This is a finally independent. What does that mean? sorry, a lot of definitions today, is finally independent if the difference, let's say P1 minus P naught, P2 minus P naught, PD minus P naught are linearly, I mean, to be careful, this is a set thing, right? A set is linearly independent in Rn. So if you look at the displacement vectors that are just formed from connecting the dots, if you will, none of them are linearly dependent. And it suffices to just look at the difference relative to one base point P naught. Okay, so by the way, notation, we'll keep using this notation. If you do square brackets S, like this is the convex hull of S. For example, in my example over here, I could say that P is equal to the convex hull of P naught, P1, P2. Okay? Where again, the convex hull is defined by taking linear combinations where the coefficients are non-negative and sum to 1. By the way, it's something kind of perverse about saying that T naught, T1, and T2 are barycentric coordinates. This is a two-dimensional object, and we're giving it 3 coordinates. Seems kind of greedy. Huh. Sorry, just saying. All right, let me get back on track here. So a convex hull is defined as such. You can take any finite set of points and calculate its convex hull. If well, next definition. If S is a finely independent set of points in Rn, then the convex hull of those points is an simplex. It's a simplex. P is a simplex. Because you can see that if you look at the line segments that are formed from, P2 minus P1, P naught, and P1 minus P naught, those are linearly independent. The edge vectors are linearly independent. Excuse me. You can also see from the triangle why it suffices to look at the differences of P naught, right? You don't need to look at P2 minus P1. If there's a linear dependence between the 3 points, it'll be picked up on by the successive difference of these two things. It's kind of interesting. Logically, before the fact, I might expect you have to look at all possible differences of distinct pairs in the set of points. But whatever. Okay, so this is a simplex if the number of points in S, which is denoted in Renteln by vertical bar S. I mean, I guess this is dangerous because you might think it's the sharp, but really this wouldn't make sense. What's the, sharping a set of points? I mean, that's just whatever, that's nonsense. So, I think. So I will sometimes use number because I like that. I mean, I think, good grief, I mean, for cardinality, is there a better notation for cardinality than that? I think it's a good notation for cardinality, personally. I don't know why more people don't use it. There must be some reason. I'm not nuanced enough in my view. We should use vertical bar, which we use for 30 other things. Okay, anyway, so if this is equal to d plus 1, then that makes this simplex a d simplex. All right? For example, over here we have 3 points. This is a 2 simplex. So I don't want to be accused of not giving you examples today. Some examples. 2 points. 3 points, we already got them, but I'll do it again. So here's a 1 simplex, aka a line segment, a 2 simplex, also known as a triangle, and a 3 simplex, possibly non-regular tetrahedron, right? I mean, I'm not assuming it. These points don't have to be equidistant or anything like that, yeah.
Is the way you drew it, the simplex is a lot like just two simplexes?
I'm indicating, well, I'm trying to draw it in 3 dimensions, so. Sorry, these two you could fit in, well, I mean, you could fit this in R. You could fit this in R too.
You're drawing a pyramid, right?
Yeah, that's a pyramid. I mean, so here we have our, let's say we have, let me do it this way. Rn, n greater than or equal to 1, n greater than or equal to 2, n greater than or equal to 3. Because I simply can't have 4 points whose 3 successive differences of one base point are linearly independent unless I have at least 3 dimensions to work with. In other words, I can't put a 3 simplex in 2 dimensions.
Are there also infinite hyperplanes for simplex?
Yeah, I mean, you could look at literal planes as the supporting hyperplanes of a tetrahedron.
But with the idea that like it only has to touch it or receive it.
Yep.
Like,
So yeah, for the 3 simplex, we could just touch a vertex, we could just touch an edge, or we could just touch a face.
and then with the idea that you can just touch a vertex, could you just like rotate a little bit around that vertex?
Yeah, there's a lot of different, if you want to describe it in terms of all of the hyperplanes which support it, it's kind of complicated. There's a lot of them. Yeah, there's infinitely many. Yeah.
So you're talking about like
Totally agree.
supporting hyperplanes, like so these planes they can't just cover these objects.
No, again, the supporting hyperplane has to be such that the whole polytope is on one side. Yeah.
So for that one up there, would you get the faces as well?
What's that?
Like the whiteboard, would that be a supporting hyperplane?
If we were viewing it in 3 dimensions, I suppose that's true. There's also the hyperplane, which has the whole thing in it. Yeah. Yeah. Okay, so fun fact: if S is independent, then T, a subset of S, also independent. Again, I'm talking about affine independence here. That's pretty nice, right? So what does that mean? So if you look at the convex hull of T, it's going to be some subset of the convex hull of S, of course. And so basically what's going to happen here is that the convex hull of a subset is going to determine a face of the simplex. In particular, if the number of things in T is equal to k plus 1, then the simplex determined by T is a k-face. Sounds like you have to really do some work to make that an insult. Like, what do you think of Cindy? She's a k-face. Two-face. K-face is 2 faces, higher dimensional, trans-dimensional analog. So special cases, 0 faces are vertices, 1 faces are edges, and n minus 1 face is a facet. All right, let's go on. phone? What'd you guys do to my phone? Oh, nothing, right? All right, so orientations. You stole it, did something to it and put it back? Sounds like something you might do. Let's see here. Orientation. Well, no, first. Sorry, first, what's a simplicial complex? A simplicial complex. What's that? Use big K to denote it. It's a finite collection of simplices such that two conditions are met. One, if you have a simplex S, generated by S, okay, convex hull of S, which is a simplex, is an element of this K, and if you have T as a subset of S, then the face generated by T is likewise an element of the simplicial complex. In other words, if the simplex is in the simplicial complex, then so are all of its faces. Okay. For any two simplices which overlap, well, if you have S1 and S2 are both in the simplicial complex, all right? And again, I mean the convex hull generated by S1, the convex hull generated by S2, and if they overlap, right? So if S1 intersects with S2, then that is equal to the convex hull of their intersection. All right. There's a way of saying this. Let me translate those more. Well, I already translated. Every face of a simplex is also in the simplicial complex. And the other thing is basically just saying that overlapping simplices meet along mutual faces. So let's see here if I can think of something. So if this was some kind of picture of K, you could think of this as being like S1, this as being S2, right? Then the intersection of S1 and S2 would be that, I'll make a dotted line, right? So you would also need that, I guess I need to give these some labels, P0, P1, P2, P3. So, the S1 intersects with S2, and I'm saying that S1, S1 is P0, P1, P2. S2 is P1, P2, P3. All right. So S1 intersect S2 is just the set containing P1 and P2. All right. So in order to have a simplicial complex, you have to have both the triangles, the edge which joins them, and also all their edges and all their vertices. There's lots of things in the complex. It contains not only the largest dimensional objects, but it also contains edges and vertices, right? Possible. Well, according to these two conditions here, right? Now the dimension. What should the dimension of K be? To be more specific, it's equal to the maximum dimension of this such that S is in K. So you look at all possible simplices in K and you pick the maximum dimension. It's a finite collection, right? So it's got a maximum. For example, my example is a simplicial complex of dimension 2. All right. Excuse me. Oh, man. Okay, so orientation. how do we define oriented simplex? What's an oriented simplex? So here's an example. We can take 2 points, P0 and P1, and I'm just drawing them twice. All right. And you can either go left to right, or you can go right to left. This is the notion of orientation. It's the set of points plus a direction, right? So our notation is that this is P0, P1, whereas this is P1, P0. And we're going to soon be we're going to build algebra over these things. And the simple convention is that P1, P0 is equal to minus P0, P1. By the way. Okay, so definition. An oriented simplex is simply a simplex where the set of generating points is assigned an order. All right, so is this shocking? An oriented simplex. And we'll use sigma bar. So P0, P1 dot Pn is a simplex, right? So it's the convex hull of these points where the order of the points is fixed up to an even permutation. Now, I don't want to get too overly technical about permutations in here, so what I'll do is I'll illustrate by an example. If you know what permutations and their signs are, I mean, I guess I've kind of done some of that somewhat technical with the wedge product stuff, but so if you think about this, right? P0, P1, P2, P0, P1, P2, right? I can either think about it oriented in like a clockwise sense or a counterclockwise sense. So like, you know, here counterclockwise, clockwise. And so this one would be, the ordering is, let's say P0, P1, P2, whereas here we have P0, P2, P1. Now these are not unique representatives, right? I mean, really we're working with an equivalence class to represent this one, this particular two simplex with either orientation. Like what else could you write here? What's that? 1, 2, 0. And what else? All right, and over here we could do very good. And if I wanted to connect these two, what would I do? What's our algebraic? I mean, there's two choices of orientation for a given simplex, right? Once you define one to be positive, the other one's negative. So the relation between these in terms of the algebra is this. This is equal to minus that. This is equal to minus, I mean, it's the negative orientation.
Kind of like the product where you start with one of the order.
Yeah, kind of like that, but these are sets of points. I mean, why should it be anything like the wedge product, right? No, I wasn't being sarcastic. Okay, so we can define a vector space here built from formal linear combinations. So here's the definition. What's an M chain? If K is an oriented simplicial complex, what's an oriented simplicial complex? It's just what it sounds like. It's a simplicial complex where every simplex in the complex is oriented. Then an M chain with coefficients in R is a formal linear combination and here it's denoted C bar is equal to a sum over I of A sub I. This is a finite sum because the simplicial complex has finitely many simplices in it, right? Okay, so like that, where the A sub, A sub I is real values, okay? Again, if sigma I and sigma j are both the same simplices but with different orientation, then they're equal to minus. If we reverse the orientation of any simplex in this oriented simplicial complex, then we get minus, right? That's the other thing here. I'm just following along. All M chains on K form the vector space CM K. So really this is just a definition, all right? What it's saying is you can take these objects, these simplicial complexes, right? And you can define an abstract vector space where the addition is defined as such. And when we formal linear, I mean, essentially, if you were to add a C bar and a B bar, what would you do? You just add coefficients, right? Where the addition would look really trivial if there was no overlapping of the complex. If they shared a complex in common, then that coefficient would get added. I mean, it's essentially the same structure as polynomials. You just add coefficients where they overlap, and if they don't overlap, you just add them. It's a vector space. This really is essentially a definition, though. Okay. Definition then.
So where does M come into play?
Well, if the simplicial complex only has, say, up to 3 chains, if it only has up to 3-dimensional simplices, then I can't look at a 4-chain, for example.
Right, but you didn't use it in your definition.
Oh, yeah. I'm sorry.
So it's all the M bases.
Sigma bar I are M simplices. Thank you. Got lost in the shuffle there somehow. All right, so here's the definition. If we have an oriented n simplex, sigma bar, p naught, p1, da da, pn, an oriented m simplex, then the boundary, partial sigma bar, of sigma is an n minus 1 chain defined below. So partial sigma bar is equal to a sum j equals 0 to n minus 1 to the j power bracket p naught da 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 pj with a hat over it. And this is a hat that you don't want to wear. If you wear this hat, you're deleted. So like, if you ever find yourself wearing this hat, it's very unfortunate. It means you're gone. You've been deleted. But not forgotten. Good point, yeah. So it's like death with a memorial or something. Huh, interesting. I like that. No, I don't like that. I don't want you guys to die. Not yet, anyway. All right. Okay, so I think examples are helpful. What's that? Here, let's use it properly. No. No, wait a minute. Wait a minute. Wait a minute. It's too good. It's too good for it. This is how we should, this is how that should be. See? No. No! So.
I can show you how to draw a duck after that.
How to draw a duck. Thank you. Okay, so the boundary of, how about P naught P1? What's this equal to? It is P1 minus P naught. If I have 3 points, let's say P naught, P1, P2, and I look at the boundary on P naught, P1, P2, I get, so let's see here, I get P1, P2 minus deleted it, right? And then plus P naught P1. Zero, 1, 2. J is the thing which is not.
And we're always going in order as if it's going from P to
So P0, P n are negative.
No, they're deleted. That J goes from 0 to n.
Then how did you pick that j equals 1? On that calculator?
That's when P1 is deleted.
Oh, you were trying to delete P1.
Everything gets deleted somewhere in the boundary operator. I delete the 0th point, I delete the 1st point, I delete the 3rd point in this example. And I go plus minus, plus minus, plus minus, plus minus.
So you're always going to delete n minus 2 points in every single boundary.
I delete 1 point.
Which in this case is n minus 2. Would you delete 2 points if it was 4 points?
I always delete 1 point. It's always going from an n simplex to an n minus 1. I mean an n chain to an n minus 1 chain. Right.
Oh. So
I mean, I've defined it for a simplex, but then we linearly extend this to get m chains. M chains are sums of simplices, so we just linearly extend this rule to get m chains, by the way.
So if you were doing a 4-point one, each one of your individual
Yeah.
would be 3.
Yeah, we can do that. But before we do that, I want you guys to just stop and smell the roses here for a bit. Now, my arrow would be what? I said P naught, P1, so it's like I draw an arrow like this, right? But if you pay attention, this is P1, P2, plus P2, P naught, right? Plus P naught, P1, where I got rid of the minus by disorienting, reorienting, blah. Come on. Look at it, though. Look at it. It's so beautiful what this is. It gives you the natural boundary of the triangle by an algebraic procedure. If we were to try to do this for a tetrahedron, that might actually be interesting.
What's the significance of the minus sign for the negative one?
I mean, that's what it takes. I mean, that's part of the definition. As you can see, it was needed in order to pick up the natural boundary, right? I mean, you can ask why it's there, but I would ask what would happen if it's not there. If it's not there, I wouldn't get what I would consider the natural boundary to the triangle, which we talk about in, like, for example, calculus 3. Imagine walking along the edge of the thing, and it has to be on your left, right? I mean, correct? It's doing that. If we were to be so foolish as to try to words. So let's say P naught, P1, P2, add a fourth point, P3. So I'm of course viewing this. And if you were to look at the boundary of, so P naught, P1, P2, P3, I'm just putting them in that order. You don't have to put them in order like that, by the way, guys. I'm just doing that for the sake of not going nuts with the formula here. So this would be what? This would be, P1, 2, 3 minus P naught, P2, P3 plus P1, P2, P0. What do I got? P0, P1, P3, right? And minus again P1, 2, 3? No, P0, 1, 2. Now let's see here. If I just flip a couple things here, I got P1, P2, P3 plus P2, P naught, P3 plus P naught, P1, P3 plus P1, P naught, P2. Let's see if we can visualize those on the tetrahedron. This 1, 2, 3 guy. Where is that? 1, 2, 3, right? So if I use the right-hand rule, right, it looks to me like we are describing the inward pointing orientation of the tetrahedron here. If I'm right, if we're describing the inward pointing orientation, if I look at the front face, the P naught, P1, P2, if I want to be inward pointing orientation, I better do like this. Is that what I have over there? 0, 2, 1, right here. And you can check the other faces. These will all give you the inward pointing orientation for the 4 faces of the tetrahedron. Well, I have 1, 0, 2, but that's equal to, you can. It's an even permutation to get to this, or you could just write this as that. I mean, whichever way you want to look at it. 2. There are 2 choices for orientation because it's a question of permutations. Once you pick one orientation for the simplex, right? Everything that's related to that by an even permutation has the same orientation. And then you have odd permutations, so there's just two.
For some reason that isn't right. If you have like.
So we can't have like an object up there, and we can't have like P2, P1, P2, P3, and then like the red arrow like reversed. Like that would be like a different combination of orientations.
Well, that would not be a natural orientation for the tetrahedron. So it's a natural orientation for the tetrahedron. And I'm not talking about the solid tetrahedron. I'm talking about the union of its faces, all right, the boundary of the tetrahedron, really. It's only a natural orientation if the orientation for the boundary is induced from the orientation for the solid tetrahedron through the boundary operator. And this is making that precise. Although, admittedly, we can only do it for these kind of polyhedra. I mean, these things with corners and faces, right? The next step in this story is to allow these to go through some sort of like warping to let them be curved. And then, so you can take a curved space, and if you can find a one-to-one correspondence between the curved space and one of these simplicial complexes, then you've got what is called the triangulation of the space. And it's through that triangulation that we want to carefully define the integration of forms over. But it all goes back to this basic idea of the boundary operator. Now, theorem. And this will make you happy, Jess. So you were right. It is a lot like wedge products. In fact, this partial is a lot like D. Quite a lot. And the proof is on page 141 of Renteln. I don't think I'm going to do it today, actually. It's not that hard. It's basically you take it twice, and you take your sum, you break it into I less than j, you break it into I greater than j, and you relabel and add, and it cancels out. It's almost the same argument we had for d squared equal to 0 if you look at it. It's more fun to just do it for examples. What's partial squared of p naught p1? Here. What's the boundary of p1? What's the boundary of p naught? Yeah, these are by definition 0, so that's kind of not an interesting one. If you look at the boundary squared of this one, it's kind of more exciting. So you get what? You get p2 minus p1 plus p naught minus p2 plus p1 minus p naught. You get 0. See, because p2 minus p1, p2 minus p naught minus p2, p1 minus p naught, the p naughts cancel, the p1s cancel, the p2 cancels. So what's the boundary of the boundary? 0. Here it's 0. In other contexts, you might want to say it's empty. All right, let me move on here. So, like I was just telling you, if you have a topological space, right? If you have a topological space X, X, a topological space, K, an oriented. Actually, it doesn't even need to be oriented. Let's just say a simplicial complex. The orientation matters to us to integration. It doesn't matter to the homology, as it turns out. Not something I'll prove in here, but nevertheless true. A topological space, if K is a simplicial complex, then K is a triangulation of X if K is homeomorphic to X. there does seem to be a slight abuse of language here. On the one hand, I'm talking about K as a collection of simplices. On the other hand, I'm talking about K as a point set. I think when I talk about K as a point set, I'm talking about it as being the convex hull of all the points which are contained within the simplicial complex, right? So it's like, it is what it has to mean, let's say. So, not all spaces are triangulable. There's something he mentioned. There's something called E8 space, which is a topological space, but it doesn't permit a triangulation. However, smooth manifolds admit triangularizations, so good news. But this is a rather special case in the larger story of topology. Right? Not all spaces can be triangulated. An example he gives, but I'll just give it too because it's an example, but we'll actually get into some details here in a second. If sigma bar is equal to p naught dot p n, if well, that is a triangulation of the n+1 ball. Let's say bn plus 1. And the boundary of sigma actually is a triangulation of the n sphere.
Is this triangulation or triangularization?
Sure.
Is it the same thing?
I think triangulation is fine. I think probably one of the things I'm saying is a mispronunciation. I'm not sure which. Okay, so excuse me. Excuse me. Yeah, triangulation. Okay. Very good, very good. Now, I guess I don't need this anymore. Let me erase it. So we can define two different kinds of chains over the simplicial complex. If you look at the M chains on the simplicial complex, there are two natural ones to look at relative to this boundary operator. So simplicial homology. So if we have an M chain, C bar with the boundary of C bar equals to 0, then C bar is an M cycle. The set of all such things is denoted Z sub M of K. These are the M cycles of the simplicial complex. 2, if you have an M chain C bar prime, for which C bar prime is equal to partial, let's say, B bar for a M+1 chain B bar, then C bar prime is called a M boundary. So you have cycles and you have boundaries. The set of all boundary all boundary chains, all such things we denote B sub M K. So this gives you a way of talking about two chains being homologous. If I have two chains which differ, all right, by a boundary chain, then they're said to be homologous. In strong analogy to we talked about cohomologous forms. Now we're talking about homologous forms. Cohomology was based on something that went from P forms to P+1 forms. You notice now the operator around the operator on the complex around this whole theory is built. The boundary operator goes the opposite way. You go from P-1 m minus 1 chains to m chains. So it's going the opposite way of D. All right. That's why this is a homology theory, whereas the other one was a cohomology theory. Now the homology is just this, H sub m of k is equal to the quotient of the m cycles over k by the m boundaries over k. So this is the mth homology group over k. By the way, definition, the dimension of the mth homology group over k is equal to what's called beta sub m in Renteln. This is the mth Betti number. An interesting application of that, in the next section, he shows you that the Euler characteristic is an alternating sum of the Betti numbers. So Euler characteristic has to do with counting faces and edges and vertices of a polygon. It's the most familiar Euler characteristic, but this gives you a way of generalizing the Euler characteristic to arbitrary dimensions in terms of an alternating sum of Betti numbers. That's in section 5.3. Now, this one? Betti number, B-E-T-T. Mth. All right. There's two ways I could go at this point. I could spend the last 20 minutes of class showing you an example of how to calculate the homology of some space, right? And that might be fun. Or I can show you what is the generalized Stokes theorem and how it works, how it relates to different things. I probably should behave and show you the example in the homology. I'm not going to behave. I will come back to calculate the homology of the circle next class, all right? So let this settle in. Next time we're going to come back, I'll try to calculate the homology for a circle, all right? It's in Renteln. It's example, 5.4. I'm planning to work example 5.4 at start of next class. What I want to do is just, at the moment for the remainder of class, just kind of take a look ahead to what we're trying to prove next class. All right, I want to present to you the generalized Stokes theorem. So I'm shifting gears here a bit. Apparently, I just reached my limit for topology in a given class. All right, so generalized Stokes theorem. What does it say? So one of the things that we're going to describe next class is carefully how do you define the integration of a form over a subset of Rn. It's basically built around using these chains we've been talking about. But just to get to it, here's what it is. If you integrate a p-form alpha, right, over the boundary of a certain manifold, it's equal to the integral over the